Okay, let's just start. Share. Yeah. So second order circuits are when we have circuit which has two types of the energy storage elements. Yeah. When uh, one moment. Yeah, for example, here the inductance and the capacitance, and of course the other passive element, yeah, the resistor, yeah, the conventional resistor. So let's observe, yeah, these two examples of circuit. In the left side, we have current source, which are the current source is connected in parallel, yeah, with resistor, inductance, and capacitance. Okay, so it means all these four components, the current source, resistance, inductance, and capacitance, has the same voltage. On the second example, yeah, on the right side, we have voltage source FST, which is located or connected in series, yeah, with resistor, capacitor, and inductors, which means that all the four has the same current flowing through them. So in the first circuit, in which we have the same voltages here, and the currents are being branched into the four or into the three RL and C, we can use Kirchhoff current law KCL with single node pair to determine the current flowing through the resistor, inductance, and capacitance. Yeah, the IR, IL, and IC. So using KCL, then putting positive side for current leaving the node, yeah, this node, the upper node, then we can write the KCL equation minus IS, minus because the IS here is entering the node, so it means in terms of leaving, and it has negative sign. Then plus IR plus IL plus IC equals to 0. Then after that, we use the respective laws for each of the components to express the current. Yeah, in the current that flows through the resistors can be calculated and can be expressed in terms of the voltage using the Ohm's law. So IR equals to VT divided by R, the voltage at that node, divided by the resistance. IL, the inductance, the current flowing through the inductance, can be calculated using the integral form of inductance law. Yeah, IL equals to 1 over L integral Vt dt or Vx dx, yeah, from t0 until t. The current flowing through the capacitance can be expressed using the differential form of the capacitance law. Yeah, IC equals to C dV dt. Okay. Then we put these three laws in expressing the currents flowing through the respective components into the KCL in the first line. Yeah, so the IS is moved onto the right hand side of the equation. Then the equation becomes V divided by R plus 1 over L integral Vx dx from with the border from t boundary from t0 until t plus C dV dt equals to IS. Since this equation still contains integral and differentiation, yeah, we can simplify it by differentiating each of the term, yeah, one time. So it becomes then dVt, yeah, 1 over R dV dt. Yeah, this is the middle term. The 1 over L integral Vx dx becomes V over L, yeah, the integral Vx dx differentiated becomes just V, yeah, V over L, while C dV dt become C d square V dt square. Then Is becomes dIs dt. So as we observe here, now this becomes a differential equation with having two order. So this is a second order differential equation. And this is the reason why this circuit is called a second order circuit, because after deriving the equation to express the relationship between the current and the voltage, then that equation is expressed or simplified into second order differential equation as shown here. Okay, so this part. Then what about the second circuit now? The second circuit is a voltage source connected in series with resistor, capacitance, and inductance. Let's use Kirchhoff voltage law, yeah, to express the relationship between the current IT, which goes through this series component, these components in series, and related with the voltage of each individual component. So here VST, yeah, if we make this loop, yeah, what do you call it? Clockwise loop. So from here, minus from the first component, the voltage source, minus Vs, plus Vr, plus Vc, plus Vl, this is Vl, equals to 0. Then we express each of the voltage using the respective law for that particular component. So the VR can be expressed using the Ohm's law as equal to resistance times current, Ri. The Vc can be expressed using the integral form of capacitance law, equals to 1 over C integral Ix dx, yeah, from T0 until T. And the VL can be expressed also in the using the differential form of the inductance law. VL equals to L di dt. Okay. Then from here we substitute this into the KVL in the first line, so that becomes Ri plus 1 over C integral Ix dx from T0 until T plus Vc T0, okay, plus L di dt equals to Vs. Okay, so remember that when we have integration, yeah, when we have integration, this this is from the initial value of the voltage. Yeah, I forgot. Yeah. This one also the current is the initial current value. Yeah. So then we differentiating again, because this equation still contains an integral form and a differential form. We make integration differentiation, so this becomes R di dt, this term. This becomes 1 over C I. Yeah, so or this one, I over C. Differentiation of this over T will be 0 because this is a constant basically. And this term becomes L di square d square I dt square. This term, yeah, equals to dvs dt. Yeah, so this again is basically a second order differential equation. That is the reason also why this circuit is a second order circuit. So again, to summarize, the left-hand side circuit, we have a current source connected in parallel with resistance, inductance, and capacitance, and we obtain the second order circuit to describe this circuit as C d square V dt square plus 1 over R dV dt plus V over L equals to dIs dt. The second circuit, we have a voltage source connected in series with resistance, capacitance, and inductance. And hence we can express the equation for the circuit as also another second order different circuit, but different term, different coefficient. L d square I dt square plus I R d dt plus I over C equals to dVs dt. Okay, let's give an example to write a differential equation for voltage T and current IT respectively. So we have here a current source connected to voltage, inductance, and capacitance. At t equal to 0, this is disconnected. So at t, before t equals 0, this is connected. So what does it mean? Before t equal to 0, all the current flows through only this circuit, because this is short circuit. Yeah, the current does not flow in the other three branches. When the current is, when t equals to 0, this is disconnected. Okay, so current starts to flow through the resistor, the inductance, and the capacitance. On the second circuit, this is a voltage source. They connected in series with RL and C. However, at t equal to 0, at t before 0, this is connected like this. This is charging. At t equal to 0, this is switch here, so disconnected from the voltage source. Okay. So the current IS at t less than 0 will be equal to 0, right? IS is the current flowing through the three parallel components, because since this is short circuited, all current from this current source will flow through this wire. At t larger than 0, IS will flow to this branch, which has these parallel branches of this resistor, inductance, and capacitance. Model for the RLC parallel is the same as what we have derived in the previous slide. For the left side of the picture, C d square V dt, d square V dt square plus 1 over R dV dt plus V over L equal to dIs dt. Okay, so dIs dt is when t is larger than 0. Okay, so when this is disconnected, equals to 0. Why is that? Because when this is disconnected, right? This flows. This is a constant, right? This is a constant. It means that its variation over time is 0. The derivative to time is 0. So this equation can be further simplified into C d square V dt square plus 1 over R dV dt plus V over L equals to 0. On the right hand side of the circuit here, we have series circuit of voltage source in series with RLC. So at t less than 0 is connected like this. The Vs equals to this Vs, right? The large Vs from t less than 0. At t larger than 0, this is short circuited, so Vs equals to 0. Yeah, this is grounded to this ground. So the model for the RLC circuit, same as what we have derived in the previous slide. L d square I dt square plus R di dt plus I over C dVs dt. So at t larger than 0, since here Vs is 0, so it means dVs dt also will be 0. So this equation can be further simplified into L d square I dt square plus R di dt plus I over C equals to 0. Yeah. So this is how we derive differential equation, considering the switching condition at t equals to 0. So this can be simplified by in the left side of the circuit, dIs dt can be simplified into 0 at t larger than 0 because this is a constant. Well, on the right side of the circuit, dVs dt can also be simplified as 0 because at t larger than 0, Vs here equals to 0. Okay, so this differential equation describe the circuit, yeah, as a second order circuit because they are second order differential equation. Then what is the solution to this differential equation? What will be then the response, the current, the IT? What will be the voltage from these circuits? So we have to go back a little bit to mathematics, yeah, to calculus and engineering mathematics to find the solution of second order differential equation. So first we have to express the differential equation, the second order differential equation in its standard form like this: d square x t square. So the second order part has the second order term has coefficient 1. 1 times d square x dt square plus a1 dx dt. The first order part has coefficient a1 plus a2 xt, and the zeroth order part has coefficient a2 equals to ft. Ft here is the forcing function. So the solution can be described as xt equals to xpt plus xct, where xp is the particular solution from the boundary conditions that are given in that particular problem. Xc is the complementary solution. So the complementary solution should satisfy the homogeneous condition where the forcing function goes to 0. Yeah. So d square xc dt square t plus a1 dxc dt, c here represent complementary, plus a to xct equals to 0. So the complementary solution xct is the solution when ft equals to 0, when the forcing function is 0. Or in other words, it is basically a homogeneous solution. If the forcing function is a constant, ft is a constant a, for example, so xp, the particular solution, xp will be equals to a divided by a2. A2 here is the coefficient of the zeroth order term, the xt. The proof is, so when xp, yeah, so this is when the forcing function is constant, xp equals a over a2. So it means dxp dt, yeah. So it means this is a constant, right? dxp dt will be equals to 0, right? d square xp dt square will also be equal to 0 because it is constant. The derivative of a constant over time is equal to 0. It means what is left is only the zeroth order term, a2 xp equals to a. Let's use pen here. So if this is 0, this is also 0. So then a2 xp equals to a, the constant. So xp equals to a over a2. Okay, this is special condition when the forcing function is equal to 0. Equal to constant. Yeah, a. For any forcing function ft equals to a constant, it means then the general solution xt will be equal to the particular solution plus the complementary solution. Or complementary here means the homogeneous solution. Okay, so then xt will be equals to a over a2, yeah, the particular solution like this, plus xct, the complementary solution. Let's now try to find the homogeneous solution. So when the forcing function equals to 0. Okay. So in normalized form, this homogeneous form equation form can be re-expressed as d square x dt square plus 2 zeta omega n dx dt plus omega n square xt equals to 0. Okay. And this you have learned also in the lab, yeah, in the lab session. So omega n here represents the natural frequency, the undamped natural frequency of the second order response. Zeta represents the damping ratio. Zeta represents the damping ratio. So this we can express this in terms of characteristic equation by replacing the differential term as s. Yeah? So d square x dt square becomes s square, dx dt becomes s, and xt just becomes 1, okay, because it is considered as constant. So we rewrite the normalized form in terms of a characteristic equation become s squared plus 2 zeta omega n s plus omega n squared equals to 0. So from here, then we can relating it with the homogeneous equation here, we obtain the A2 equals to omega n squared, or the undamped natural frequency equals to square root of A2. Yeah. A1 equals to zeta 2 zeta omega n, right? 2 zeta omega n, which means that zeta equals to half of A1 divided by omega n, right? Half of A1 or A1 divided by 2 divided by omega n. Substituting the value of omega n from the previous equation here. So zeta equals to A1, the coefficient here divided by 2 divided by square root of A2. Okay, this is the general equation. So what is the proof? I will not explain to detail here because this is actually part of the calculus and engineering mathematics. So please ask Pak Fatoni or Pak Agus Suhaimi. We will more focus towards its implementation, application in solving second order circuit. Okay, so we just use this, yeah, this relationship to find the omega n and zeta of the response solution to that second order circuit. So for example, we have derived the equation for a second order circuit and we obtain this second order equation for d square x dt square t plus 8 dx dt plus 16 xt equals 0. You are asked to determine the characteristic equation, the damping ratio, and natural frequency. So if you look at the characteristic equation, the coefficient for the second order term should be made into 1, right? Only then that we can find A1 and A2. So it means to make the coefficient of the second order term to be 1, we have to divide each of the term with 4. So this is divided by 4, this is divided by 4, divided by 4, this is divided by 4. Then it becomes d square x, yeah, secondary d square x dt square plus 2 dx dt plus 4 xt equals 0. This is already in the standard format, standard form of characteristic equation, right? So this can be rewritten as s square plus 2 zeta omega n s plus 4 equals to 0. Yeah, 4 becomes the A2 and 2 here becomes the A1. Okay, s square plus 2s plus 4 equal to 0. So from here, yeah, the s square comes from d square x dt square, s comes from the dx dt. Okay, and xt becomes 1. To find the damping ratio natural frequency, 4 equals to the omega n square, right? Yeah, the A2 is 4, yeah. So the omega n equals the square root of 4, which is 2. Then 2 zeta omega n equals to 2. Yeah. So we obtain omega n equals to 2. 2 zeta omega n equals to 2. Zeta omega n equals to 1. So zeta equals to 1 over omega n, or 1 over 2. Zeta equals to half from here. Okay, it's not that difficult, yeah, in the for the implementation. So this is the important formula which we need to pay attention, yeah, to solve the response of the second order circuit, as long as we have made the equation into standard characteristic equation, which means that the coefficient for the second derivative term must be made into 1. Okay, let's go further with analysis of homogeneous equation. That is when the forcing function equals to 0. So in the normalized form, d square x dt square plus 2 zeta omega n dx dt plus omega n square xt equals to 0. Okay. So xt, the solution, yeah, xt equals to k, a coefficient, times exponent s and t is a solution if with double f, yeah, not just single f. What does it mean? If double f means if and only if. So actually, if with double f is a contraction or abbreviation for the term if and only if. Yeah, it means that this is true with the condition of this, but also vice versa. This condition is true when this condition is fulfilled. Okay, so this condition is true. S square plus 2 zeta omega n s plus omega n square equals 0 is true only if the solution xt equals to k, a component, a constant, times exponent of s n times t. Okay. If double f, s is a solution of the characteristic equation, then the proof is dx dt will be equals to s, here s times k times exponent st, d square x dt square will be equal to further derivative of this one, s square k exponent st. So if we write again the equation, this equation, d square x dt square t plus 2 zeta omega n dx dt plus omega n square xt, this equals to this part, yeah, s square k exponent st plus 2 zeta omega n sk exponent st plus omega n square exponent k exponent st. So the term k times exponent st can be put outside the bracket using distributive law. Yeah, so the term inside becomes s square plus 2 zeta omega n s plus omega n square times k exponent st. So this is really the solution of this homogeneous equation. Yeah. So the characteristic equation will be equal to so this equals to 0, right? Because of this term. So this equals to 0. So in order that this equal to 0, this term has to be equals to 0, because this cannot be 0, yeah, because exponent, the value exponent cannot be 0 if exponent of 0 is 1. Okay, so this value, the characteristic equation s squared plus 2 zeta omega n s plus omega n squared has to be 0. So from there we try to find the roots of this equation. Yeah, this is equals to s plus zeta omega n square, yeah, s square plus 2 zeta omega n s plus zeta square omega n square. Okay, plus this term omega n square minus omega zeta square omega n square. Let's try to find out. So this becomes s square plus 2 zeta omega n plus zeta square omega n square plus this one omega n square minus zeta square omega n square. Okay, so these terms cancel each other. Okay, so this becomes s square plus 2 zeta omega n plus omega n. Okay, so it's correct. Yeah, this equals to 0. Okay, so from here, then this can be further simplified, yeah, using S equals to this one goes to the right hand side, zeta omega n square plus omega minus omega n square. Yeah, this go to the right hand side, becomes zeta square omega n square minus omega n square. So then you make square root of it, so that this become equal to S plus zeta omega n, so, equals to plus minus square root of zeta square omega n square minus omega n square. The terms, this one then move to the right hand side equation, becomes negative zeta omega n plus minus square root of zeta square omega n square minus omega n square. Omega n square can go out of the square root term and become omega, minus zeta omega n plus minus omega n square root of zeta square minus 1. So this is called as the modes of the system. Yeah, the solution of the characteristic equation from the second in the case for the homogeneous equation, yeah, where the forcing function equals to 0. Now the first case is when zeta is larger than 1. Yeah, when zeta is larger than 1, this is larger than 1. So this value becomes positive, right? So S becomes equals the root is real and distinct root. Real and distinct root. We have two roots. S1 equals minus zeta omega n plus omega n square root of this one, yeah, because it's a number, a positive number, right? Because zeta square larger than zeta is larger than 1, so zeta square minus 1 will be a real number. Then the second root is minus zeta omega n, negative omega n times this root, times this value. Then the solution will be equals to xt, yeah, equals to k1, since we have two distinct root, yeah, s1 and s2, right? The solution xt becomes k1 exponent s1t plus k2 exponent s2t. Case 2 is when the value zeta is less than 1. So zeta square minus 1 will be negative value, right? This value will be negative if zeta is less than 1. So what is the consequence of that? Then this is the value of this is negative, and the square root of negative is an imaginary number. So the root becomes a complex conjugate root, yeah, minus zeta omega n plus j omega n with that number of the square root, yeah. J here, the imaginary part. S2 will be equal to minus zeta omega n, negative j omega n, and the value of this root, zeta square minus 1. Okay, so if xt equals to k1 exponent s1t plus k2 exponent s2t, and s1 and s2 are complex and conjugate roots, so when exponent times complex, exponent, for example, a plus j b, right? This is can be re-expressed as cosine and sine. Yeah, later we see. So S will be minus zeta omega n plus minus j omega n square root of minus 1 minus zeta square. So omega n times square root of 1 minus zeta square can be simplified as we define a term called omega d, the damping ratio, right? The damping frequency. So S equals to minus sigma plus minus j omega d. Omega d is the damped oscillation frequency, where sigma is the damping factor. So when xt is real, here the K2 is the conjugate, yeah, of K1. Conjugate means that if K2, if K1, for example, is minus sigma plus j omega d, K2 will be minus sigma minus j omega d. It will be on the different in the upper part and the lower part of the complex plane, the complex plane. So xt here, yeah, then can be expressed since it is in conjugate, yeah, we can express it in cosine and sine. Xt equals exponent minus sigma t, yeah, sigma the damping factor, so it's minus, so that's why it is going to decay, yeah, going to decay, times a1 cosine the damping frequency omega dt plus a2 sine omega dt. Yeah, so this is derived from a exponent st, yeah, exponent s exponent minus zeta omega n plus minus j omega dt. So this equal to exponent minus zeta omega n t times exponent minus plus j omega dt. Okay, this term become this one, exponent minus sigma t. This term become the cosine and sine term. Okay, this one, exponent minus plus j omega dt. Yeah. Here, exponent minus plus j omega dt equals to cosine. Remember, this is from Euler's rule, yeah? Euler's rule in engineering mathematics. So exponent x equals to cosine, exponent j x equal to cosine x plus j sin x. Okay. So similarly here, exponent minus plus j omega dt equals to cosine omega d t minus plus, because of this, yeah, j sine omega dt. Okay, so far clear? Any questions? Hello? No response?
No, sir.
So
No question.
ready for quiz for second order?
No, sir.
No, not ready to, sir.
No, sir.
Yeah. If no response, then it means ready.
Not ready, sir.
Okay, so let's continue first. Yeah, not yet finished the explanation. Okay, assuming that K1 from this equation equals to A1 plus J, A2 divided by 2. Okay. It means since K2 here is the conjugate of complex conjugate of K1, yeah, K2 is a complex conjugate of K1. Yeah, this is sign of conjugation. And since S equals to minus sigma plus minus j omega d, yeah, this is the root. It means that xt will be equals to, yeah, 2 real times K1. So we replace K2 with the conjugate of this. So means this becomes K1 minus JA2. K2 becomes, let me just add it down. Conjugate of K1. So K2 equals to K1 minus J. K2 divided by 2. Okay, divided by 2. Since xt here, equal to exponent minus sigma dA1 cos omega dt plus A2 sin omega dt, then xt can be re-expressed as the real part of k1 exponent minus sigma plus d omega dt exponent minus st. Okay. Then I have to erase. Case 3 is when zeta square equals to 1. When zeta square equals to 1, it means this term under the square root becomes 0, right? Since 0, this s becomes only equal to minus zeta omega n plus minus 0. Yeah. So you have only single root basically, or you have two but equal roots. S becomes equal to minus zeta omega n. Yeah. So xt equals to b1. The general solution for xt for this homogeneous equation becomes b1 plus b2. B1 plus b2t times exponent minus zeta omega n t. Because s is only this minus zeta omega n t. So t exponent st is solution if and only if s squared plus 2 zeta omega n s plus omega n squared equals to 0. Okay, so this is the characteristic equation. And n means both term have to be true in order that t exponent st is the solution. And 2s plus 2 zeta omega n equals to 0. 2s plus 2 zeta omega n equals to 0. Okay. Okay, let's have a break for 10 minutes, and we will continue in the second term about deriving the solution for the